Let's start the Q&A session. So who starts the question? Yeah, Lee.
Professor Wang, thank you very much for the excellent talk. I'm really impressed with how powerful the STM technique combined with the electrochemistry. In particularly, you show us that you can form molecular wire using the technique. And you also show us that you can change the molecular identity of some of the molecule. Well, does it mean that actually, let's say after you form the wire, you can change a middle part of it to form a transistor or something? Have your team tried this?
Yeah, I think this is a very good question and a very important suggestion. You know, in my group, we can only do some electrochemistry measurement and so can do some electrochemical deposition. That means we can prepare a lot of different pattern and different nanowire, but we don't know how to prepare device. So that's a very big pity, I think. Now I'm looking for the collaborator. In particular, recent year, we also prepared a lot of two-dimensional organic covalent material on the surface. Not like, almost like graphene structure, but is not a single simple atomic structure. Well, it means composite by atomic, by atom, just by the molecule. And also it's a very hot field now. Now the problem in my group is how to measure the conductance of the two-dimensional organic materials. So if some people can do this, I'd like to have collaborate with them. Okay.
Professor Wang?
I also like to follow up on this in situ SPM. So you showed very clearly how the image of graphite in the lithium-ion battery case, and it's a sub-nanometer, 0.2 nanometer resolution. I was just wondering how difficult is it to image lithium? And if you can do that, you can study, of course, the lithium ionic transport. That would be fascinating.
Yeah. I think this is a very good question. I think first, if you want to get atomic resolution image, the surface will be very flat. And second, the SPM can image only some stable species. If the species move too fast on the surface, we cannot see. In the lithium-ion case, because this guy moves on the surface very fast, maybe some process happened, but we don't know. But I'm sure in the SEI film, some lithium-ion will be there. Okay.
Okay. Next question.
What I don't understand well is about the technique, about the SPM technique for electrochemical reactions. Actually, one of the advantage of SPM is the high resolution, and in some device they have to do the experiment in vacuum to get high resolution. But in your case, it's even in solution in the liquid. So what I'm wondering that is, you show some very good high resolution image. What I'm wondering is that, do you need to select some specific system for some molecules to get this image, or the technique can be used to get high resolution image for any kind of system after optimization? And also I'm wondering, like for example, in the solution, if you move the tip of the SPM, that the liquid will just flow, right? This seems lots of problems here. So any comments, any explanation?
Okay. First, I think you just worry about the movement of tip in solution. Maybe the tip just like a stick, so the surface will become very complicated, and the imaging also very difficult. But I'd like to tell you, no any problem. So you can get a very stable image. As I said, if you just buy the commercial equipment, maybe some problem. But we just improve the commercial equipment. So now we can get a very stable STM imaging solution during the scanning. This is the first question. And the second, for the organic molecular study, I think this technique is much useful compared with UHV SPM system, because the sample preparation in the electrochemical system and the UHV system is totally different. In the UHV system, the people usually use two methods. First is evaporation in situ. In that case, some molecule can be evaporated, and some molecule cannot be evaporated. If you evaporate some molecule in vacuum, the molecule will decompose it. This is the first. And the second method, just deeper the molecule, deeper the solid substrate in solution, and then take the solution and put this sample into UHV chamber. In that case, and then you have to get a high vacuum environment in the chamber. Yeah? In that case, some molecule on the solid surface will also just how to say, if the molecule have a very strong interaction with the substrate, the molecule will remain on the surface during the vacuum preparation process. If the solution is very weak, if you prepare the high resolution, high vacuum environment, the molecule will be dissolved from the surface, so nothing can be seen. So in this point, I think the electrochemical preparation, I mean in our system, no this limitation. Just very simple, just put it in the solution and then you can see. Okay.
Okay. Other question? Yeah, Professor Wang Ning.
Yeah. Well, you show a lot of data of the molecules on gold 111 surface.
Yeah, yeah.
Will the other surface of gold play the same role or get the same results?
Yes, no. First, I think the surface pattern, the surface structure is depend on mainly the molecular structure. And the second, the substrate, the different substrate are also very important. The same molecule sometimes maybe can get the same structure on different substrates, but usually it's different.
Right. For example, the nanowire structures
Yes,
you
yeah.
form on gold 111.
Yeah.
But if you use graphite or graphene surface, you may not get the wires,
Yes,
right?
yes, you are
so
right.
it's the substrate dependent, right?
Yes, yes.
Thank you.
Yes. But however, you can, if you want to get some nanowire, you can just design or use the different molecule on different substrate.
Yeah.
Thank you very much for the interesting talk. I am interested in the SEI formation on the cathode material, the lithium nickel manganese oxide. As you know, the material is a very high voltage material, so you expect electrolyte decomposition during charge and discharge. I'm wondering, when you do your ECSPM, if you do more cycling,
Yeah.
do you see growth of the SEI layer? And does it make a difference if you have the 111 surface versus the 100 surface?
I think, usually the first cycle, the SEI will be formed. But in this case, for example, maybe in the first cycle, the thickness of the SEI may be 4 to 5 nanometer. And then you can continue the cycle. But the thickness of the SEI will be stable, I think about after 10 or 20 cycles. Yes, no.
Okay. Other question? So, last question.
Yes, thank you. It's a very nice talk, Professor Wan. I'm concerning about the part of lithium-ion battery. So you mentioned that the germanium carbon graphene composite. So why the stability of germanium carbon graphene is better than germanium carbon, but the read performance of germanium carbon graphene is it looks like worse than the germanium carbon?
Yes, because I think the main problem for these materials is first is conductivity, conductance. That means the transfer. But if you use the double protection, the transfer will be very good. And also another problem is stability. That means after the charge and the discharge process, the pure and bare germanium will be, how to say, the structure will be damaged and will be damaged and not so stable. If you covered by by the double protection, you can get like perfect electrode materials.
Okay. So thank you very much. So let's thank again Professor Wan.